So this video is looking at the first of the section B questions. There's only 3 of those, the longer calculation questions. I'm going to talk you through it step by step. Doesn't mean it's the only way of doing it. If you want to fast forward to the end and see if you're right, that's great. If you're coming here because you tried to do it and you looked at it and decided it was too hard and you wanted to look at the answer, go away and try it and put some answers down. Stop chickening out. If you're not doing it while you're practicing, you're not going to do it in the exam. So go back and have a go. It doesn't matter if you make a mess. Let's get going. So now I'll tell you the answer, assuming that you've come back and tried it. We've got an unknown compound, compound Y, but we do know it contains carbon, hydrogen and oxygen, which could be important. And we are trying to find out the molecular formula of Y. So we've got some information about mass, about volume, and about temperature and pressure. So that immediately tells me there's going to be some sort of ideal gas question. Then we have some separate information about a different sample, burnt in oxygen, and we're given the masses of carbon dioxide and water. So that sounds like I'm going to need a balanced equation and some sort of mole calculation. And it says calculate the empirical formula and the molecular mass. Now actually it doesn't matter which way round you do this. So I'm going to start with the ideal gas information first, because it's probably easier to get your head round. So again, always think of which bits you can do of a question. Just because you may not be able to access the whole 10 marks right now, doesn't mean you can't do some of it. So we're going to use the first bit of information first, but you could have done this the other way around and it'll still work. So don't worry about which order you do things. Maths is maths. So we've got a mass, we've got a temperature, we've got a volume, pressure. So we know we're going to need to use PV equals nRT. We're going to write that down because often it's worth a mark for remembering the relationship. And if it's not worth a mark, it would definitely be worth a mark for rearranging it to find N, which is the number of moles of Y. If I know the number of moles and the mass, I can work out the molecular mass of 1 mole of Y. So I've got N equals PV over RT. There's my T. Temperature in 100 degrees C needs to be changed to Kelvin. So I add 273. You might have added 0.15 on that, that's fine. 200 centimetre cubed, that needs to be in meters cubed. And there are 1,000,000 centimetres cubed in a meters cubed, or 10 to the 6. So I'm going to do 200 over 1 times 10 to the 6. And that's going to give me 2 times 10 to the minus 4. You may have been told to just write 200 times 10 to the minus 6 in your calculation, and that's absolutely fine. In fact, it's a good way of doing it because it's something that you do all the time in an ideal gas question. Just be careful though in case they give you dm cubed instead of cm cubed. Then it's 10 to the minus 3. Kilopascals, 95 kilopascals, needs to be turned into pascals. So we times it by 1,000 and we get 95,000. So I'm going to put all of those numbers into the ideal gas equation. It might seem that you're thinking, well, why? If I've already written them down somewhere else, why do I have to write them all in? Well, you probably wouldn't have written them up in the question, so you should be writing them in the equation right now. You should be writing them because if you miss a 0 or something else goes wrong in your calculator, but you wrote down the correct things to put into the equation, you will get some marks for doing that, even if it always happens, you know, the button slips, you miss a number on a calculator, and it's hard to self-check these because they're unfamiliar numbers. Let's have a look at our number of moles. It comes out as being pretty small. I'd expect it to be pretty small because it's a pretty small mass, 0.540 grams. So that's fine. That at the moment makes sense. It's going to make a lot more sense when we put it into the equation to find the relative formula mass, the MR, for that compound. So now I have number of moles. All I've got to do is just rearrange the standard equation for moles, mass and MR. MR is how many grams there are per mole. So it will be 0.54, the number of grams, divided by 6.13 times 10 to the minus 3 to get me the mass of 1 mole of Y. And that equals a nice round number of 88, which is a sensible number for a molecular mass. Now, in theory, I know it contains carbon, hydrogen, oxygen, but there is no way I could tell the molecular formula just from that. There are many, many combinations of the masses of carbon, hydrogen, and oxygen, which could add up to 88. So therefore, we're going to need to go to the other piece of information to work out the empirical formula. What we need to know now is what is the relationship, what's the ratio, carbon, hydrogen, and oxygen in that compound. But it's not a straightforward empirical formula question, because instead it's given it in the form of combustion. This will actually become more common next year when you do more organic synthesis and analysis. This is quite a much more common way of phrasing it. Just because you haven't done it though doesn't mean you can't attempt it just from your own knowledge of moles, because all it is thinking about the balanced equation. So for combustion, if I know that, I don't know, I've got X, Y, Z amounts of C, H, and O. If I react it with oxygen, I know I'm going to make CO2 and water. That is a given for combustion of any organic compound. So, what else can I know? Well, I know that for X carbons, I will make X carbon dioxides. Standard balancing procedure. 1-to-1 ratio. I know that if I have Y hydrogens, it's not quite so straightforward because water has the formula H2O. And so therefore, for every Y moles of hydrogen, I'm going to be making Y over 2 moles of water. How many oxygens do I have? I have no idea. We can't deal with everything all at once, and that's something that people do too much in a calculation. They worry about all the bit stuff down the line. Just concentrate on what you do know already. Well, what do we know? We know some masses. We know masses, we can work out some moles. That's a given. So let's have a look at the masses we've been given in the question. So we've been told the mass of Y, the original sample, which contains carbon, hydrogen, and oxygen. But more importantly, we've been given the mass of carbon dioxide collected and the mass of water. So if I know mass of any compound, and I know its formula, which I do for CO2 and water, and I know for Y, that means I can work out number of moles. Can't work out number of moles of Y. Well, actually I can, because I know it weighs 88, but that's not going to help me much because I just don't know what the ratio of X, Y, and Z are. So I'm going to look at the CO2 and the water and then work out the moles of each of those compounds. So the MR of CO2 is 44. 7.92 over 44 is going to give me 0.18 moles of carbon dioxide. The MR of water is 18. 3.24 divided by 18 gives me 0.18 moles of hydrogen. So far, actually, what I've done is I've reached a point almost with an empirical formula where I almost have a mole ratio of carbon and hydrogen. But I need to be a little bit careful because moles of carbon dioxide does equal moles of carbon, but moles of water does not equal moles of hydrogen. So what it's telling me about Y is that 3.96 grams sample of Y contains 0.18 moles of carbon, and it contains 0.36 moles of hydrogen. So the ratio between carbon and hydrogen is 1 to 2. So I'm 2/3 of the way through finding the empirical formula, which means I'm very close to working it out. The problem is I don't know how much oxygen there was in my 3.96 gram sample. But I do know how many moles of carbon and how many moles of hydrogen there are because I just worked it out. So if I want to know how much mass is oxygen, I now need to work out how much mass in that sample was carbon dioxide, it was carbon, sorry, and was hydrogen. Not was carbon dioxide, not was water, I've already got that. I need to know where, how much carbon there is in that original mass, and how much hydrogen there is in that original mass. So, mass of carbon. There's 0.18 moles of carbon, and 1 mole of carbon weighs 12. So, working that out, that tells me there is 2.16 grams of carbon in the sample. Seems sensible. The good thing is it's not more than 3.96, otherwise I've done something wrong. The mass of hydrogen in that original sample, well, I have 0.18 moles of water, which means I have 0.36 moles of hydrogen. Remember, 2 moles of hydrogen. 1 mole of hydrogen weighs 1, not very difficult. So that's going to tell me that I've got 0.36 grams of hydrogen in the sample. So I now know the total mass of the carbon and hydrogen in my 3.96 grams. So therefore my mass of oxygen atoms is going to be 3.96. Take away the other two, the amount of mass for the carbon and the hydrogen. So you can only really do this question with quite simple organic compounds that only have, say, 3 elements in them. Sometimes you may have carbon, hydrogen and sulfur or something like that, but you'd have to know everything that was created then. So it's 1.44 grams of oxygen was what we just worked out. So now I'm going to turn it back into a straightforward empirical formula question. So my mass of carbon, this is the mass of carbon, not the mass of carbon dioxide, was 2.16. My mass of hydrogen was 0.36, and therefore I worked out my mass of oxygen was what was remaining, 1.44. I don't need to calculate my moles of carbon because I already did that in the previous example, and I already calculated my moles of hydrogen. So I'm only doing this to show you how it's like an empirical formula question, but also to show you that we need to calculate the moles of oxygen now. So moles of carbon and hydrogen we already knew, that was from the water information and carbon dioxide. Moles of oxygen we can now work out 1.44, divide that by the atomic mass of oxygen, which is 16, and that will give me an answer for oxygen, which is going to be 0.09. Lovely numbers. If I got really weird numbers out of this, I'd be going back to check them, because I know that this empirical formula needs to fit into 88. I know that it's got to have reasonable numbers. I'm not expecting anything weird. So C2H4O was my empirical formula, and I know that the molecular mass was 88. So I've got everything I need to work out the full molecular formula of Y. So I'm going to work out the mass of 2 C's, 4 H's and 1 O. That adds up to 44. And so therefore that goes into 88 twice. So the total formula, the molecular formula, is C4H8O2. So the thing to take away from this question is that even if you looked at it originally and it seemed like a lot of unknowns and a lot of information that you weren't sure where to go with, there was clearly an ideal gas question in there, which is usually worth between 4 and 5 marks on its own. And there was clearly a mass question, something to do with moles and mass. So always go with trying to write an equation. And if there's anything you don't know, put some algebra in there, like X and Y and Z, to think, well, maybe if I don't know exactly what it is, but I know what the relationship is between them. And just whatever you can do. If you're given the mass in grams of anything in a question, carbon dioxide and water, you can immediately calculate moles, even if you get stuck from there. So it's not necessarily about getting 10 out of 10 every time. It's about doing little steps and doing as much of the question as you possibly can in order to build your confidence and be able to tackle these questions. And the more times you do them, the better you're going to get at them. Any questions? You're going to write them down Anything you still don't understand or want to know where other examples of this, whatever questions you've got, just send them to me at cksciencetuition@gmail.com, and I'll try and handle those in the YouTube session at the end of the week. Otherwise, if you haven't already done so, have a go at questions 2 and 3 of section B, or have a go at the multiple choice questions as well.